Hello guys, this is K. Rekha from Sri Venkateshwara College of Engineer. Today we will discuss about poisonous distribution. Contains what is poison distribution, understanding the poison distribution formula, real world application of poison distribution, limitations of poison distribution, formulas on poisonous distribution, poison distribution versus normal distribution, conclusions. What is poison distributions? Poison distribution is a statistical concept that helps us understanding the likelihood of the rare events occurring. It was the first introduced by the French mathematician Simon Dens-Fanchon in the earlier 18,000 century. The distribution is used to model the number of the times on events occurs within a specific time or space interval. Next, the Poisson distribution was many real-world applications such as predicting the number of the customers who will visit a store in a given hours or estimating the number of the defects in a manufacturer. It was also commonly used in the healthcare to predict the number of patients who will arrive at a hospital during a specific time period. Next, next we will discuss about understanding the Poisson distribution formula. The Poisson distribution formula is a mathematical tool used to model events that occur randomly over time or space. It calculates the probability of the certain number of the events occurring within specific interval or real given the average rate of occurrences. Here, the formula itself is relatively simple. P of x is equals to k iteration lambda and lambda goes to k, where lambda is the average rate of occurrences and k is the number of the events being modeled. To better understanding this formula, let us consider an example. Suppose we are interested in modeling the number of the customers who entered a store in a given hours. If we know the average rate of the customers enter in a 10% hour, we can use the Poisson distribution formula to calculate the probability of the certain number of customers entering store during the hour. For instance, the probability of the exactly 5 customers entered the store could be P of x is equals to 5 and calculate 0.037. Next, we'll discuss about real world applications of the Poisson distributions. In a finance, poisonous distributions can be used to model the probability of a rare events such as market crashes or extreme price movements. These informations can be used to the manage risk and make informed investment discussions. Next, the healthcare poison distributions can be used to model the number of the patients arriving at a hospital in a given time period. These informations can be used to optimize suffering levels and allocate resource efficiency. What is the limitations of the poisonous distributions we will discuss? Well, poison distributions can be useful tool in a many sensors. It is important to understanding its limitations. One key limitations is that is assumes even occur independently of each other, which may not always be the case in real world situation. For example, if we are tracking the number of the car accidents on a particular road, the occurrences of one accident may increases the likelihood of another accident happening soon after. Next, another limitation of poisonous distribution is that is assume a constant rate of occurrences over time or space. This means that is may not be opportunity to use in situation where the rate of occurrences varies the significantly. For example, if we are tracking the number of the customers enter a store throughout the day, we may use a higher rate of occurrences during a peak hours compared to off peak hours. Next, we'll discuss about the formulas on poisonous distribution. First, in case of to compute mean mu, if frequency are given, mu is equals to sigma f of I xi by sigma f of I. Second one, the mean of the poisonous distribution in the form of the binomial distribution m minus np. Third one, the poisonous distribution is given p of x is equals to m to the power of x e to the power of minus m divided by x. Next, we will discuss about problems on poisonous distribution. First, fit a Poisson distribution for the following xi 0, 1, 2, 3, 4, fi 122, 60, 15, 2, 1. Formula mu is equals to m is equals to sigma f of I xi divided by sigma f of I, where sigma f of I xi is equals to 0 plus 122 is 0 plus 1 plus 60 is 60 plus 30 plus 2 is 30 plus 6 plus 4 is equals to 100. Next, sigma f of I is equals to 122 plus 60 plus 15 plus 2 plus 1 is equals to 200. Next, m is equals to 100 divided by 200 is 0.5. The Poisson distribution. Here we will use the Poisson distribution formula. P of x is equals to m to the power of x e to the power of minus m by x is equals to 0.5 to the power of x e to the power of minus 0.5 by x, where 0.606 into 0.5 to the power of x by z, let x is equals to, we taken 0, 1, 2, 3, 4. Now we'll do 4 iterations. 0.606 bracket 0.5 to the power of 1 divided by 1 is equals to 0.303 divided by 1 is equals to 0.303. Next, we take the second 0.606 bracket 0.5 to the power of 2 divided by 2 is equals to 0.151 divided by 2. Next, 0.7575 is equals to, now we take the third 0.606 bracket 0.5 to the power of 3 divided by 3 is equals to 0.0126. Next is equals to 4. 0.606 bracket 0.5 to the power of 4 divided by 4 is equals to 0.0016. Conclusion. In conclusions, we have learned that Poisson's distribution is a powerful tool for a modeling the occurrences for a rare events. By understanding its the formula and application in various fields, we can better analyze the predictor real world sensors. Next, it is important to keep in mind the limitations of the Poisson distributions and to consider other distributions such as normal distributions when a prosperate, however, within participated the veracity Poisson's distributions remains a valuable tool in a data analysis and discussions making. Thank you.